Hello and welcome to our lesson on diode practice questions. To summarize the theory lesson we did on diodes, a diode can either be placed in forward bias or reverse bias. And the definition of forward bias is if the current is flowing out of the battery this way, and you see the diode drawn like so, you assume the examiner is telling you the diode is in forward bias there. If the diode is instead drawn like this, that is a diode in reverse bias. And the behavior of the diode changes depending on the bias it's put in. When the diode is in forward bias, like this, that's another way of saying there is a positive voltage across it. So the voltage here is higher than here. The potential difference across here is higher than here. So we look at this section of the graph to see what behavior the diode obeys. And we can see that no matter how much voltage we try to push across this diode with the battery here, the diode never wants to accept more than 0.7 volts, say if it's a silicon diode. This value can change. If it's a germanium diode, it might not be 0.7, it could be 0.3. But the gist of it is it's fussy. It'll do everything it can to only accept this amount of voltage. Now, reverse bias, that is this region of the graph. And that indicates there's a negative voltage across it, which just means the diode is pointing in the opposite direction. And the voltage here, the voltage here is higher than the voltage here. The graph shows the behavior of the voltage. No matter how much of the behavior of the diode, no matter how much voltage, the magnitude I try to put across this diode here, it never wants to actually let any current through. Notice the diode in forward bias has no problem letting a lot of current through. But in reverse bias, it's not the voltage it's worried about, it's the current. So think forward bias, it's obsessed with the voltage it wants. In reverse bias, it's obsessed with the current it wants, and that current is effectively zero. In reverse bias, you can also think of it as just another resistor, but with a resistance of, say, 10,000 ohms, something very, very large. That's just a tip if you're ever trying to work out how a circuit would behave with the diode in that configuration. So looking at a practice question now, with a diode in forward bias. Say I had a 12 volt battery here, and this diode obeyed the rule set out by this graph, and the resistor had a constant resistor of 100 ohms. And the question simply asks how much current is going through the diode. The first thing to note is that these two components are in series, therefore the amount of current going through the diode is the same as the amount of current going through the resistor here. The second thing to note is that the diode, as always, is very fussy about the amount of voltage it wants to receive. It only wants to receive that 0.7 volts. Now the third thing, since these two components are in series, they must have 12 volts between them. If 0.7 volts is lost to the diode, that must mean 11.3 volts is left over for that resistor there. And look now, we've got a resistance, we've got a voltage, so we can use Ohm's law to figure out the current flowing through that resistor. V equals IR, V on R equals I. V on R is equal to 11.3 over 100, which is actually 0.113 amps. So that is the amount of current flowing through that circuit there. Moving on to another similar question, in which we have the same 12 volt battery, but two different values here. Now we have only a 0.6 volt diode, and we actually don't know the resistance through that resistor. all we do know is that we're seeing a current, this time we're being given the current, of 6 milliamps through the circuit. So step 1, we make the same assumption before. These two components must have 12 volts between them because there's being 12 volts being supplied by the battery and it has to be used up over here. So this component again has 11.3 volts across it. And we also know the current flowing through here is the same as the current flowing through here. So the current is equal to 6 times 10 to the negative 3 amps. I'm putting it in amps because we're going to use Ohm's law in a second. Getting now the resistance by itself, that was the goal, finding the resistance of that component. V on I is equal to R, voltage 11.3 over 6 times 10 neg 3 is equal to, I'll use my calculator, 11.3 divided by 6 neg 3. I have that as 1883 ohms. And I know it's in ohms because I've used volts and amps over here. The final question. This I haven't seen come up a lot, but it is a curious type of question to ask, and I think it could be assessed. It's when you have, first of all, a resistor here in a simple series arrangement, and then you have a small parallel section of the circuit. One of the branches has another simple resistor, and the other branch has a diode in forward bias. Both resistors have a resistance of 100 ohms. The diode is this type of silicon diode, and the voltage is 10 volts. The goal is to figure out the amount of current flowing through here. I'll do that in green, I think. I is equal to. So first things first. This diode here always wants to receive that 0.7 volts. Since these components are in parallel, that means that the voltage across this component must be the same as the voltage across this component. Just like when you have a regular circuit with two resistors in parallel like so, you assume these two get the same amount of voltage. So there must also be 0.7 volts across this resistor here. And left over for this resistor up here, we must have 9.3. And I'll add a second challenge. We're also going to figure out how much current is flowing through there. But the amount of current flowing through here is also the same as the amount of current flowing through here. So we use V equals IR, V equals 9.3, R equals 100, V on R equals I, 9.3 over 100 equals I, which is equal to 0.093 amps. So there's 0.093 amps flowing through here. We expect that current to split up down one of those two paths. And the amount of current here, using our common sense, is going to be less than 0.093. Let's use Ohm's law here. V equals IR, V on R equals I, 0.7 on 100 equals I, which is equal to 0.007 amps. And there is indeed less current flowing through here than here. And the last question, the bonus question, is how much current is flowing through there. We don't actually know the resistance of that diode. So we can't use Ohm's law over there. What we can do is say the 0.093 amps that were flowing through there splits off. So we get 0.007 amps flowing down there and the rest flowing down here. the rest of that current is the answer we want. So the amount of current here is equal to 0.093 take away 0.007. And that comes to 0.086 amps. I hope this video helped in solving some of these tricky diode circuit questions.